Chapter 11, Hearing. So, there's two definitions of sound that you need to understand, and two ways of viewing sound. The first is the actual physical definition. Sound is nothing more than sound pressure changes moving through the air or water or other medium. That's all it is. It's just energy rippling through a medium such as air or water. Sound is also perceptually what we experience when we hear something. More specifically, it's what we experience when we actually are in the presence of these physical sound pressure changes that are flowing through a medium. All right, so there's two different aspects to it: the actual physical aspect of sound and the perceptual aspect of sound. The way speakers work, even the speakers that you're using right now to listen to my voice, there is, even in the headphone or in your computer, on your phone, there is a diaphragm. It's a membrane made of plastic or cardboard that can move in and out very quickly. So it can move in and out very quickly. So when it moves out, it pushes air molecules out, and that condenses them. So it's called condensation. And when it pulls back, it creates a little vacuum. So it pulls the molecules apart, and that's called rarefaction. So you have these alternating condensation and rarefaction that produces the sound waves that you ultimately hear, that travel through the air and you ultimately hear. So here's a picture. Here's a speaker sitting on a table, and the dark areas represent the condensation where the air has been compressed, and the lighter areas indicate where sound has been decreased, or the air molecules have been decreased in rarefaction. So sound travels through the medium much the way waves travel through the surface of water when you drop an object into the water. And ultimately these vibrations of the air, ultimately they make their way to your ear, and that's the beginning of the process of you experiencing hearing. Pure tones. Pure tones are created by a sine wave. And a sine wave is a wave that looks like this. It has valley and a hill, valley and a hill. That's called a sine wave. And the way we describe a sine, we use a variety of different terms to understand sine waves and sound waves, so you need to understand these terms. One of the terms that we use is amplitude, and that's the difference in the pressure between high and low peaks of the wave. So you might have sound waves that go like this, so they kind of have low amplitude, and then you'll have sound waves that go like this, much higher amplitude. We perceive the amplitude of a sound wave as loudness. So very soft sounds have very low amplitude, and very loud sounds have a much higher amplitude. There's more energy in there. The way we measure amplitude is by using a unit of measure called the decibel. The decibel. And the decibel is a unit of measure that is equal to 20 times the log of P divided by P0. Now P, in this equation for decibels, P is the pressure that we are measuring, and the pressure is measured in units called pascals. And a pascal is basically how much force is being applied to a surface. Okay, so P is the pressure we're measuring, and P sub 0 is the reference pressure. And in the case of sound, reference pressure is the lowest perceptible energy that we can perceive, and it's set at let's see, it is set at, hang on just a second, I had it in my head a right ago, 20 micropascals. So P sub 0 is usually set at 20 micropascals, and P is also measured in micropascals or millipascals if it's super loud, right? So we take however many pascals of energy are being imparted onto a surface, divide that by the reference number, P sub 0, take the log of that. Logarithms are used for really huge numbers. Logarithms are handy when you're dealing with very large numbers. That it helps. It's a way of converting a very large number into a number that's more easy to compute. And then you take the log of P divided by P sub 0, and then you multiply that by 20, and that's the number of logarithms. The take-home message really is that decibels increase on a log scale. So the more energy you put on into the decibel equation, the higher the number of decibels. But it's not a linear relationship. It operates on a logarithmic relationship, meaning that the decibels, the change in decibels represents an increase in orders of magnitude. So, for example, the change going from, let's say, 1 decibel to 2 decibels of sound is different than the amount of change going from 21 to 22 decibels in sound, because the higher you go, the more energy you're talking about. So we use decibels to relate the amplitude of the stimulus, which is measured in pascals, to the psychological experience of loudness. So basically we're taking the amplitude, the physical energy that's being transmitted through the air measured in pascals, and converting it into a number, decibels, that we relate to experiencing how loud things are. Frequency. The other thing you have to know about sine waves and sound waves is frequency. Frequency is the number of cycles within a given time period. Frequency is measured in hertz. So, for example, 1 hertz is 1 cycle per second, meaning the curve goes from here to here. I'm sorry, from here to here in 1 second. We perceive frequency as pitch. So lots more of these waves crush per unit of time is a higher pitch, and fewer waves per unit of time is a lower pitch. I have here a tone generator in my phone. So this is a tone that is at 1,000 hertz, meaning that there's 1,000 sine waves per second coming at your ears. Listen. Whoops. Oh, for heaven's sake. Okay, that's 1,000, a pure tone of 1,000 hertz. And here is a tone of, oops, let's see. Oh, for heaven's sake, hang on a sec. Here's a tone of 4,000 hertz. As soon as I can get this thing to set up correctly. Here's a tone of 4,000 hertz. Now notice that the first one was 1,000 hertz and it was lower in pitch than the second one, which is 4,000 hertz, which tells us, of course, that hertz, the higher the number of cycles per second, the higher we perceive that as higher pitch. Tone height is the term that we use, that what you just experienced going from 1,000 hertz to 4,000 hertz was tone height, meaning that the pitch increased when the frequency increased. When I increased the frequency from 1,000 hertz to 4,000 hertz, you experience that as a change in pitch. So here's a nice picture to summarize this all of these concepts. So this line here, this purple line here, is a sine wave, like one complete sine wave. The up part and the down part, and then it starts up again. That is one cycle, one complete sound wave. So the tone that I just played for you at 1,000 hertz had 1,000 of these per second coming at your ear. The change is when the curve goes up, there's an increase, a slight increase in the atmospheric pressure, in the number of air molecules, and when the pitch goes, when the cycle goes down, that's a decrease in the number of air molecules, and of course we have this is all as a function of time. And this is the way sound waves are illustrated sometimes, or look sometimes, when you see the changes in energy that are being produced by the vibration of a membrane or some other thing. The dark areas indicate where the amplitude goes up, and where the curve goes up, and the light areas indicate where the decreased pressure happens when the curve goes down. The higher each wave goes, the higher the amplitude, which we of course perceive as loudness. So the higher this goes, the louder it sounds. Of course, this amplitude physically can be measured in pascals, millipascals, but we experience that loudness as we measure that loudness, experience of loudness, as decibels. And here's another example. Here's a picture of a pure sound wave that is high-pitched. Here is a pure sound wave that is kind of middle-pitched, and here's a pure sound wave that is low-pitched. Notice the unit of measure here is 1/100th of a second. So you've got basically one, two. So this is a couple of hundred hertz, right? Very low pitch, medium pitch, and then a high pitch. You have more waves per second happening in the high pitch than you do in the low pitch. And amplitude is expressed as changes in air pressure, and we perceive that as loudness. So these three waves are the same frequency, so you're going to hear these as the same frequency, but this one down here is going to be soft, this one's going to be a little louder, and this one's going to be much louder. Again, it's physical air pressure, that there's just more air being moved in the loud one, but we perceive that more air being moved as increases in loudness, in other words, increase in decibels. So the more pascals of air pressure you're moving, the louder, the higher the decibel measure goes. So here is a nice chart that gives you an idea as to the relationship between different sounds that you might hear, the amplitude, and in terms of the energy, and the decibels. So at threshold, right, where things are just barely audible, we call that 0 decibels, and we call that an amplitude of 1. If it's very quiet and leaves are gently rustling, like in the wind, that's a very nice quiet sound, and that's about 20 decibels. Being outside in a quiet residential community, generally the ambient sound is about 40 decibels. The average speaking voice is about 60 decibels, roughly around 60 decibels. Being in a subway, if you've ever been in a subway before and the train comes in, it's very loud, and that is at about 100 decibels. That's where you start getting pretty loud. The prop on a plane that's taking off, so when the propeller is spinning its fastest, It's at 120 decibels. That's very loud. This is where you start getting into some, rock concert loudness, basically. And then finally, a jet engine at takeoff. If you're standing right next to a jet engine at takeoff, without ear protection, you're going to ruin your hearing. Because jet engines are putting out 140 decibels of sound, of loudness, which is extremely loud. And of course, the reason jet engines are so loud is because all they do is move air. That's what they do. They have a big thing in the front that they have blades in the front that suck in a huge volume of air. It gets sucked in, squeezed, mixed with jet fuel, ignited, and then that explosive squeezed air is released out the back of the jet engine. And of course, sound that is moving air. So since jet engines move a large amount of air per unit of time, they're going to be very loud, and in fact they are. Notice also the amplitude changes. When we go from 120 amps, from 120 decibels, we're going from an amplitude of 1 million, and then to the jet engine 10 million. That's a factor of 10 increase. It's a huge increase, and the reason, and notice that these numbers are very big, 1 million, 10 million. In order to avoid dealing with these big numbers, that's why we take the log of the ratio between the energy being measured and the reference energy, so that we can turn it into something that we can more easily work with, that is decibels.